All right, this is Mr. Anderson for Statistics, Math 130. Today we're going to cover the confidence intervals for the mean when the standard deviation of the entire population is known. Now, when you see a survey about statistics, you should be thinking to yourself three main questions. How do these estimates that they're finding in the survey compare with the population and their percentages? So really, how close are these estimates to the real thing? What is really meant by the margin of error? So when they say something is between plus or minus 5%, what is that really talking about? And is that sample size big enough? Do they take enough pieces of data to ensure that they have everything that they need to make an assumption? Well, we're going to basically talk about some studies, and we have to make a couple of assumptions about studies. First of all, the studies have to be random samples. They can't be biased. And your sample size should at least be greater than or equal to 30. Now, if your sample size is not greater than or equal to 30, so if n is less than 30, you at least need to know that you have a normal distribution of your data. So if it's under 30, make sure that your data is normally distributed. If not, get more data. Now, some data is robust, and a robust survey or a robust result is a distribution that can depart from a normal shape. And that's if the size, the rigor, depending on how much work was done on it, can prove that no matter how big or how well the data is done, this robust data does not have a normal shape. This chapter will not be dealing with this information in particular, but it is kind of one of those three parts of the assumptions we must use for our kind of studies. What we are going to be doing, though, is we're going to be looking at a point estimate. And a point estimate is a specific numerical value of a parameter. And to translate that a little bit, point estimate is like saying we're looking for a specific number. So a point estimate is a specific number of a parameter. And a parameter is a kind of mean, it can be a median, it can be a mode. It's whatever we're talking about to try to represent the entire data. Now, for the last couple chapters here, we've been focusing just on an average. So really what we're trying to say is a point estimate is a numerical value of the average, because we're not talking about finding numerical values of medians or modes in large populations. Now, this is something to highlight here. The best point estimate, I'm shouting at you here, of mu is the sample mean x. And that would be an x with a line drawn across the top of it. So that sample mean of x, where I have just a line drawn across the top, that is what we're going to be talking about today. We're going to try to see how close can the sample mean of x get to the real value of mu. Now, because we are human and we can't actually get the actual mu for the entire population without doing some very elaborate census, we're going to come up with some good ways to get an estimator for that mu. Now, to a good properties of estimators. Here, let me get to the typing mode again. Three properties of good estimators. So first of all, a good estimator is unbiased. And that means that your estimate your estimate should be equal to your population parameter. So that means your estimate should try to be as equal to your mu as possible. So your sample mean x should try to be, as unbiased, which means it should be equal to the population parameter, or mu. All right, we're going to now go to consistent. As a sample gets bigger, the estimate gets more accurate, or gets better. So it should be, if you've got 30 pieces of data, and you find yourself getting to 60 pieces of data and your estimate's getting worse, then it's not very consistent. So you definitely want to have your data get better as you collect your data. We also want relatively, still dealing with new software here and hardware, relatively efficient. So we want your data to be relatively efficient. That means it should have a small variance. You shouldn't be picking a group and having a wide variance in it. Now, an interval estimate. An interval estimate is an interval or range of values to estimate the parameter. So we're going to come up with a range of values to estimate the parameter. And we're going to define the confidence interval as the probability that the estimate will contain the parameter. The confidence interval is the probability the estimate will contain the parameter. For much of this worksheet, I'm going to be abbreviating the confidence interval to be CI. So got to pick stylus here instead of box. So CI, or confidence interval, is going to be either one of three main intervals: 90, 95, and 90%. So in this worksheet and in many of your homework assignments, we're going to be looking for a confidence interval of 99% accuracy, 95% accuracy, or 90% accuracy. The 99% accuracy is not going to include 1% of the data. So we're not going to be talking about the top. So these are not the top nor the bottom half percents. Now, if you're thinking about, what do you mean? Don't you mean the top or bottom 1%? Well, no, because if I have 99% in the middle, if the top was 1% and the bottom was 1%, then I'd have 101%. So if I have half percent on either side of 99%, that would put me in the top or bottom half percent. So we're not looking at those, we're looking at the middle 99%. Now, try to think about this. If I'm looking at the 95% confidence interval, I don't want the top nor the bottom 2.5%, because 2.5% on top and 2.5% on the bottom would give me 100% with the 95. Try this next one. If you want a 90% confidence interval, you don't want the top nor the bottom what percent? And the answer would be 5%. Now, visual learners will get a little picture of this on the second page here, but I wanted to emphasize that when we talk about the 90% confidence interval, we want really the top 5. We don't want to talk about the top 5%, nor the bottom 5%. All right, and that will give us a better error. All right, so let's go to the second side of this worksheet here. And here's where we're going to draw some of our pictures here. Now, remembering from our previous lesson here, we had a we had some formulas to basically look at, and one of our formulas that is very important here is our formula of an error, the sample error. The sample error formula from the previous worksheet was given as the standard deviation of the entire population divided by your sample size n. So the more sample you have, the less effect it has on your standard deviation. Now, to find your confidence interval for a mean of a specific tail that we're going to specify, it's going to be our sample average plus or minus the confidence interval z-score, I'm going to abbreviate that as CI, times the sample error. Now, I'm going to show you how this all breaks down before we actually start doing a problem. First of all, your normal curve, let's draw a normal curve here. Sorry, that was maybe not as normal as it should be. In the middle of your normal curve, you have your mu, which is what we're trying to find. Remember, we're not going to be able to find it accurately because we cannot do so with 100% accuracy. We are only going to get to 90, 95, or 99%. So if we have a 90%, and I'll use decimals here, if we have a 90% confidence interval, then that middle space is 90%, which means that the tail here is 5%, and this tail here is 5% to make up 100%. So, the book and statisticians call these tails the alpha. And the alpha of this entire problem is 10%, because this tail is 5% and this tail is 5%. So the alpha of this confidence interval is 10%. 5% on top, 5% on bottom. So you'll notice that that alpha shows up right there. And this alpha right here is z-score sub alpha divided by 2, or z sub half alpha. So let's try to break this down and say what this really means. Now see, our goal here is to find our real population average, but we're not going to do so accurately because of sample error and because of our confidence interval, and we can never get that confidence interval up to 100%. So what we're going to do is we're going to go between two bounds. We're going to take our average from our sample, so we're going to take maybe 30 items, find an average, and then we're going to subtract from that to find my lower tail. We're going to subtract from that our confidence interval. Now that lower confidence interval is going to be z sub alpha divided by 2 times our standard deviation divided by the square root of our sample size. Now, you might say, okay, the problem is going to give me the standard deviation and the problem is going to be the sample size, but what am I going to use here? You're going to use whatever value from our table our confidence interval tells you. So, the number I'm going to use here for 90% is going to be 1.65. Now you might right now flip to your table and try to find the 90th percentile, like 0.9000, and you'll see that that's technically not 1.65. To find this on the z table, you would technically have to find the value that's closest to 0.95. And you're probably wondering, well, why 95? Am I looking for the 90th confidence interval? Yeah, but remember that right here, that's going to be 0.05, so that's 90 and 95. 90 and 5 would be 95%. So that's where the 1.65 comes from. If you were going to use a 95% confidence interval, then you would look up 1.96. And that's because you're going to take your 95%, so let's kind of look at that here, 95% confidence interval, this is going to be 2.5% or 0.025. Sorry, I got my zero squished there. And this is also going to be 0.025. So this is going to be on the table the number closest to 0.9750. Now, if I was looking at the 99% interval, these little tails are really small. They're only 0.5%, or 5 thousandths. So that means if I was going to look at the table for my 99% confidence interval, I'd be looking at 0.995 or 995 thousandths, 9,995 ten thousandths, and that would be 2.58. Now, going back up here, that is, since we've now discussed what number to plug in for our z here, since we're going to know these values and this, since this is a symmetrical piece of data, this is going to be the same thing on the left, x bar, and then the z sub alpha divided by 2 times our sigma divided by the square root of n. And in this case, it's going to be a plus, because this is a symmetric piece of data here. All right, so this whole thing is going to be our lower part of our margin of error, and this whole thing is going to be the upper part of our margin of error. And the margin of error is the maximum likely difference between the estimate of the parameter and the actual value. All right, this is your last chance to take a look at this. I'm going to move to my typing mode so I can type in some notes. So pause it here. All right, to get to the bottom here, the margin of error. The margin of error, when you hear about this in political polls or scientific studies, is the maximum likely difference between the point estimate of a parameter and the actual value. So what does that mean? The point estimate is we're trying to find, this is our sample mean. We can't actually get the real thing because that would be mu. So we're trying to find our difference between the point estimate of our average and the actual value, which is mu. So what we'll do is try to find some examples here, and we got some to find our best point estimate of the confidence interval for the mean. Or in other words, we're going to show you today how to find, oops, got to get back to screen mode here. We're going to try to find the best number, point estimate is a number, numerical value, of our sample mean to the actual value mu. So here we go. We had 50 cars that had an average time on the car lot of 54 days, with a national standard deviation of 6 days. Find the best point. Now, this is given in the book here, so today we're actually using standard deviations given to us. We're going to not find out about how to do these without the standard deviation given to us until the next video. And we're going to find a confidence interval of 95%. So here's what we're going to know. We know our sample mean is 54 days on the lot. So we're trying to find out the national days, the national average for cars on a parking lot. We know that the standard deviation, since it was given to us, was 6 days. The confidence interval is 95%. So we're going to look up 0.975 on our Z table. And from the worksheet up above, I told you that that was 1.96. and our sample size is 50 cars. So in the center of our data, we're going to have our good old buddy mu. Mu is going to be our answer that we can never obtain exactly, but we're going to at least get pretty close to it on either side. So we're going to take our sample average, subtract our 1.96, our confidence interval z-score, multiplied by our standard deviation divided by the square root of our sample size. This gives us 54 minus, typing this all in on the calculator, 54 minus 1.7, and then doing that gives us an answer of 52.3. So 52.3 is our bottom of the confidence interval. This is going to be basically that we know that the nation's cars stay on the lot an average between 52.3 and this upper bound that we're about to find. Now I will write this all out, but some of you will notice that this is just the same thing as the left side with a plus instead of a minus. So what this gives us then is 54 plus 1.7, or 55.7. And this here gives us that confidence interval of 55.7 and 52.3. Now, that means I'm somewhere between these two numbers here. So you might hear this simplified answer that our answer for mu is going to be 54 plus or minus 1.7. So within 1.7 of 54 is going to be that actual population average. And again, it's off a little bit because we chose a 95% confidence interval in this situation. Alright, now I'm going to leave this up here. You can pause it if you need to copy it down. I'm now going to move my screen down so it's going to disappear. Bloop. Alright, this would be a great time to pause the video and try to label all the important things in this problem. For example, our sample average, our standard deviation, our confidence interval, and the sample size, and try to do the problem out. Alright, hopefully you've worked on that and now you're checking your work. Your sample average of people waiting in this hospital is 174.3 minutes. Its standard deviation is 46.5 minutes, and the confidence interval is going to be 99%. So if we looked at 0.9950 on the chart, that's going to be a z-score of 2.58, and our sample size is equal to 30. Okay, let's put mu in the middle here, and we'll do the left tail first. We'll go 174. Looked at the previous problem there. 174.3 minus 2.58 times a quantity of 46.5. There we go. Put that decimal point there. 46.5 divided by the square root of 30, because we have 30 people in our sample. That's 174.3 minus 21.9, and that gives us 152.4. Sorry about that. 152.4. 152.4 looks like mu is that's going to be our lower end of our national average for people waiting in a hospital. 152.4 minutes. So we're going to look at the other side of this. Again, I'm going to write everything out, but some of you on your homework might be a little bit more savvy and realize that this side is just like the left side with a plus instead of a minus. And 46.5 divided by square root of 30. That's 174.3 minus 21.9, or plus, sorry, whoop. And that gives me 196.2. Therefore, we've got the average of the Americans' wait in hospitals in the emergency rooms, and this is taken from the book, so don't blame me for this data, is going to be 174.3 plus or minus a waiting time of about 21.9 minutes with a 99% confidence interval. All right, so let's move on to the next problem here. We're going to shift gears a little bit and talk about sample size. So, moving down to the last page here, sample size is really based on three pieces. The sample size is based on, let me get to my screen draw here. Okay. Sample size is based on the margin of error. Sorry, I'm going to do this freehand instead of typing. Margin of error, the population standard deviation, and the degree of confidence. All right. So these three things, margin of error, standard deviation, and degree of confidence, they're all based on the sample size. Now there's a proof in the book that describes how this equation is generated, and I strongly recommend that you take a look at this here. The formula is going to be our confidence interval, which is our z-score of alpha or sub-alpha 2 divided by 2, times the standard deviation given to you, divided by your error, the margin of error that you really want, quantity squared. So this will determine what your sample size is. So we're trying to figure out how many measurements we should take when we're measuring the depth of a river. And the scientists want to be 99% accurate within 2 feet. Now, I think you're always going to try to shoot for the most accuracy possible, but when you do so, you're going to drive up the number of measurements that you have to take. So we want to be within 2 feet of the bottom of the ocean, and the national studies have said that you're going to, using this method, your standard deviation is going to be, 4.33 feet. So they're giving you the standard deviation here. So here we go. To find n, we're going to use our z value from 99%, which we've seen is 2.58. Again, you can look on the chart at 0.995 to find that. And we're going to multiply that by our standard deviation, which is 4.33. And then divide that by our margin of error, which is 2. Now, the whole thing has to be squared. Now, if you do this on the calculator, I would strongly recommend that you do this in parts. Take your numerator, hit enter, and then divide it by 2, get the answer, and then square it, and you'll get an answer of 31.2. Now, you're always going to round up. Since this is telling you to do 31.2 measurements, you're not going to round down to 31 measurements. So you're going to round up, so your answer is 32 measurements. All right. Now what I'd like you to do is I'd like you to pause the video if you need to copy this down, but I'm going to turn this off. Okay, and scroll down. A pizza shop owner wishes to find 90% confidence interval of the true mean cost of a large pizza. How large should the sample be if he wishes to be accurate within 15 cents? And let's assume that the previous standard deviation, or our lowercase sigma, is going to be 26 cents overall. This would be a great time to pause the video and try to do this by yourself. So unpause it when you're ready to see the process out. Okay, from the start of the problem, our confidence interval was 95%. So if I look at my z-table at 0.975, that gives me 1.96. And our error, we want to be within 15 cents of the price that we want to have, and then our sample size, basically our standard deviation is going to be 26 cents. So our N is going to be 1.96 times 0.26 divided by 15 cents. That's our margin of error we want, quantity squared. Now, if you do that out correctly, you get an answer of approximately 11.54 surveys, or you would round that up, you would want to do 12 samples. 12 samples, 12 people to figure out, what kind of, accuracy you need in this situation. All right, and so that ends that. I will hope that you do the homework. If you have questions about this, please send me an email. Thank you very much.